Black holes, facts, paradoxes, and what JWST and Chandra are revealing. If you're listening late at night, let this be slow, even, and unhurried. Black holes don't need a dramatic voice. They're already dramatic in the quietest possible way, by changing the shape of space and time without making a sound. A black hole is not an hole in the ordinary sense. It is not an empty pocket carved out of the universe. It is a region of space-time where gravity is so intense that beyond a certain boundary, nothing, no signal, no particle, not even light, can escape back to the outside. That boundary is called the event horizon. It's not a physical wall. It's more like a line in the future. Once you cross it, all possible paths forward lead deeper in. Because black holes don't shine, we rarely see them directly. We infer them. We read their presence the way you read wind by watching leaves move. We watch stars orbit something invisible. We measure bursts of X-rays from superheated gas as it spirals inward. We track jets, long, narrow beams of matter and energy launched from the neighborhood of darkness. And sometimes we listen for the faint tremor of space-time itself when two black holes merge. It can help to gently correct one common image. Black holes are not cosmic vacuum cleaners roaming the universe, sucking everything into them. Far away, a black hole's gravity behaves like any other gravity of the same mass. If the sun were replaced magically by a black hole with exactly the same mass, Earth would still orbit in almost the same way. The blackness is not about stronger gravity everywhere. The blackness is about what happens at a particular radius where the escape speed exceeds the speed of light. So why do black holes feel so haunting? Maybe because they sit at the crossing of three things we care about: geometry, matter, and the limits of knowledge. They're where Einstein's general relativity becomes breathtakingly concrete. And they're also where quantum physics, our rule book for the microscopic, starts whispering questions that are hard to ignore. This episode will be calm, but it will be deep. We'll start with the foundations, how the idea of trapping light emerged long before modern telescopes, and how relativity made the concept precise. Then we'll move outward into the bright, turbulent environments around black holes, accretion disks, X-ray flares, jets, and into the instruments that help us study them. Chandra, observing the universe in X-rays, is particularly good at catching extremely hot gas and energetic processes. JWST, looking in infrared, is exceptionally strong at peering through dust and at seeing very distant galaxies whose light has been stretched into longer wavelengths by cosmic expansion. And then, softly, we'll touch the famous paradox. If black holes can slowly evaporate, what happens to the information about everything that fell in? Does the universe keep its memory, or can it truly forget? But before any paradox, there's an atmosphere to set. Imagine the universe not as a painted dome above your head, but as an ocean of space-time. Stars are bright islands of heat. Galaxies are archipelagos, and black holes are deep whirlpools, places where the surface of reality curves down so steeply that the usual routes outward simply don't exist. The strange part is that the quietest object can produce the loudest surroundings. A black hole itself emits no light, yet the gas falling toward it can glow more fiercely than entire systems. In some active galaxies, the region near the central black hole can outshine the combined light of billions of stars. Darkness, in this case, is not an absence of energy. It is a boundary condition. It is a rule about escape. Here's a gentle mental model. Picture a smooth, stretched sheet. Place a heavy ball in the center and the sheet sags. Roll a marble near it and the marble curves inward. In real physics, the sheet is space-time. The heavy ball is mass energy. The marble is anything that moves: planets, stars, even photons. In strong gravity, paths bend not because a force yanks them through space, but because the geometry of the space they travel through is different. Now take that sagging sheet and imagine the dip becoming so steep that near the center, every direction you can move forward leads downward. That's the intuitive shadow of an event horizon. You don't have to picture it as violent. You can picture it as absolute.
If you're still awake enough to answer a soft question, pause here. What draws you in more? The idea that light can't escape? Or the idea that time itself behaves differently near a black hole? If you want, leave a brief comment. Light or time? There's no right answer. It just tells me where your curiosity naturally goes. In the next part, we'll step back into history, into the early questions that led, quietly, to one of the most powerful ideas in modern science. Long before anyone photographed a black hole's shadow, the first steps were taken with a simple question: how fast do you need to go to escape gravity? If you toss a stone upward, it rises, slows, and falls back. Toss it harder, and it rises higher. In principle, if you launch something fast enough, it never comes back. That threshold speed is the escape velocity. In the 18th century, a few thinkers wondered, what if a star were so massive and so compact that its escape velocity exceeded the speed of light? If light itself couldn't get away, the star would be dark to distant observers. This was a speculative idea, and the physics of light was not yet complete, but the intuition was surprisingly close to the modern concept. The real turning point arrived in the early 20th century with Einstein's general relativity. In this framework, gravity is not a pulling force across empty space. It is the curvature of space-time caused by mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. When physicists and mathematicians began solving Einstein's equations, they found something remarkable. Even in a simple case, an idealized, non-rotating spherical mass, there exists a critical radius. If an object's mass is squeezed inside that radius, an event horizon forms. In other words, the no-escape boundary isn't just a metaphor, it drops out of the mathematics as a natural consequence. For a long time, black holes still felt like an oddity. They seemed to involve infinities and breakdowns of familiar reasoning. Some wondered whether they were mere artifacts of an overly simple model. Maybe real stars could never collapse that far. Maybe some unknown pressure or some new physics would halt the collapse before the horizon formed. But astronomy began to answer with evidence rather than imagination. By the mid-20th century, scientists discovered intense sources of X-rays in the sky, objects far brighter in X-rays than ordinary stars. X-rays often come from extremely hot gas, millions of degrees, heated by violent processes. In certain binary systems, a normal star orbits a compact companion that does not shine like a star, yet seems to draw matter toward itself. The falling matter forms an accretion disk, heats up, and glows in X-rays. The key is mass. A neutron star can be compact and faint, but it has a maximum stable mass. If you infer an unseen companion significantly above that limit, a black hole becomes the simplest explanation. Not a guess, an inference supported by orbital dynamics and radiation. From there, the case strengthened. Black holes weren't just theoretical curiosities, they were plausible endpoints of stellar evolution. When a massive star exhausts its nuclear fuel, the outward pressure that supported it weakens. Gravity wins. The core collapses. Depending on the mass, it may stabilize as a neutron star or collapse further, forming an event horizon. It's worth saying this slowly. A black hole is a kind of final geometry. It's what happens when mass energy is concentrated enough that spacetime curves into a shape that includes a one-way boundary. That boundary does not require drama, it requires density. And yet, even in calm explanation, the idea carries a quiet awe. An event horizon is a limit on communication. It's a boundary on what the universe can tell you. Outside the horizon, physics continues as usual. Stars orbit, light travels, time flows. But at the horizon, the flow of possible futures changes character. If you imagine a river approaching a waterfall, that can help you understand. Far upstream, you can swim against the current. Closer to the edge, the current quickens. At a certain point, no matter how hard you swim, you cannot escape the pull downstream. The event horizon is not the water. It is the place where escape upstream becomes impossible. This is also why black holes provoke philosophical feelings. They make knowledge feel local. You can know what happens outside. You can model what likely happens inside, but you cannot verify the inside by receiving a signal from it. There is a humility built into the geometry. If you're listening in a sleepy state, you don't need to hold every detail. Just keep the contour of the story. A simple question about escape led to a new theory of gravity, and that theory led to a boundary in spacetime. Then the sky began to echo the theory back at us through X-rays and orbital motions. Before we move on, here's a soft checkpoint. Do you enjoy the historical thread, the way ideas slowly mature over centuries, or do you prefer the modern observational thread, where instruments and data take the lead? If you want to leave a comment, just write history or data. Next, we'll turn from origins to behavior. What does matter do around a black hole? Why do the surroundings glow? And why do some black holes launch jets that cross intergalactic space like lighthouses? The most vivid black hole stories are often not about the hole at all. They're about the dance around it. Start with accretion, the process of matter falling inward. In space, gas rarely falls straight down. It has angular momentum. It's already moving sideways. So when gravity draws it to a compact object, it spirals. The result is an accretion disk, a flattened whirlpool of gas and dust orbiting at extreme speeds. Inside that disk, particles collide, magnetic fields twist, friction and turbulence convert gravitational energy to heat. The closer the gas gets to the center, the faster it moves and the hotter it becomes. In the innermost regions, temperatures can rise so high that the disk shines in ultraviolet or X-rays. That is one reason X-ray observatories are so powerful for black hole science. They can detect the glow of matter pushed to the edge of its endurance. Chandra is an X-ray telescope, which means it is tuned to some of the most energetic light in the universe. X-rays often trace shock waves, superheated plasma, and violent magnetic reconnection. When Chandra sees an X-ray flare near a suspected black hole, it is essentially watching the disk's hot skin flicker and rearrange. But not all black holes are equally active. Some are hungry and bright, surrounded by thick disks. Others are quiet, accreting very little. Even a quiet black hole can still reveal itself through subtle changes, faint flares, weak jets, or the orbital motion of nearby stars. Now about jets. In many systems, especially those with rapidly spinning black holes or strongly magnetized disks, matter is not only drawn inward, some of it is expelled outward in narrow beams from the poles. These jets can travel near the speed of light and can extend for thousands or even millions of light years, shaping the environment far beyond the black hole's immediate neighborhood. Why would a black hole eject matter instead of swallowing it all in? The short answer is that gravity is only part of the story. Rotation and magnetic fields matter too. When ionized gas orbits in a disk, it behaves like an electrical conductor. Magnetic field lines anchored in the disk can be twisted by rotation, storing energy like a wound-up spring. Under certain conditions, that energy can launch material outward along the magnetic field lines, forming a collimated jet. There are different theoretical mechanisms proposed, but you don't need to memorize names to grasp the intuition. A spinning, magnetized system can convert rotational and gravitational energy into organized outflow. In that sense, the black hole is less like a vacuum cleaner and more like an engine hidden behind a curtain.
This matters on cosmic scales. Jets can heat the gas in galaxies and galaxy clusters. They can prevent gas from cooling and forming new stars. Or, in some circumstances, they can compress gas and trigger star formation. In other words, black holes can help regulate the evolution of galaxies. The central darkness can influence the long-term weather of cosmic environments. If you like metaphors, imagine a city at night. The city center might be a dark park, but the roads around it glow with traffic. And sometimes, from the center, powerful spotlights sweep outward, visible from miles away. The park itself is dark. The activity around it is bright. That's what accretion and jets feel like. There's a calm lesson here. Black holes are not simply destroyers. They are transformers. They convert the energy of falling matter into radiation, heat, and organized motion. They are laboratories for plasma physics, magnetism, and relativity. Places where nature runs experiments at scales we cannot reproduce on Earth. If you're listening with one foot already in sleep, just keep one image. A circular disk of glowing gas turning smoothly around an invisible center, like fog lit from within. And above and below that disk, a thin, straight beam reaching outward, steady and serene.
as if the universe is drawing a line through its own darkness. Here is a gentle question to place in the margins of your mind. If the most luminous things in the universe can be powered by the darkest things, what does that suggest about the way we define presence and absence? If you want to comment, you can keep it simple. Darkness can shine, or light needs dark. Next, we'll talk about how we confirm black holes through observation, through orbiting stars, through X-rays, through images of shadows, and through the quiet music of gravitational waves. A detail worth adding, because it is both scientific and soothing, is variability. The light from an accretion disk can change on timescales that range from minutes to years. Short timescale changes suggest that the emitting region is small, because a large region cannot brighten or dim all at once. So timing becomes a kind of ruler. When X-ray light flickers rapidly, it hints that the action is taking place very close to the event horizon, where orbital periods are short and magnetic fields can rearrange quickly. This is part of what makes X-ray astronomy feel like listening to a heartbeat. The disk brightens, fades, brightens again. Not because the black hole has emotions, but because plasma is turbulent and because gravity is strong. Even in turbulence, patterns emerge, and those patterns can be measured. If you want one more calm picture, imagine a record player in a dark room. The record is the disk. The needle is our telescope. The music is the light curve, rising and falling with subtle rhythm. The record is spinning whether or not we are listening. Our job is simply to record the song and learn what the song implies about the unseen turntable in the center. In the next file, when we talk about evidence, keep this in mind. In black hole science, we often use time itself as a measurement tool. A good scientific question is often a practical one. How do we know? With black holes, we rarely get a single, unmistakable photograph that settles everything. Instead, we build a case from multiple kinds of evidence, different languages that all describe the same hidden object. One classic line of evidence comes from binary systems. Picture two stars orbiting each other. If one of the companions is invisible, no star-like light, no visible surface, we can still infer its mass from the orbital motion of the visible star. The star's speed and orbit size are controlled by gravity. Measure those, and you can estimate the mass of the unseen companion. If the inferred mass is too large to be a neutron star, the simplest remaining explanation is a black hole. That is not certainty in the absolute sense, but it is the kind of strong inference that science relies on. Alternatives become increasingly implausible. A second line of evidence comes from radiation, especially X-rays. When gas falls toward a compact object, it heats up. Around black holes, the heating can be extreme. The inner accretion disk can glow in X-rays, and the glow can fluctuate as the disk's magnetic fields rearrange. Chandra's strength is its sharp X-ray vision, which helps astronomers separate different sources in crowded regions and track changes over time. A third line of evidence is the imaging of a shadow. This can sound paradoxical. How do you image something that emits no light? The answer is that you don't image the black hole directly. You image the bright background around it, and you see a dark silhouette produced by the bending and capture of light. The gravitational field warps the paths of photons in such a way that a shadow appears, an outline of the region from which light cannot reach the observer. The striking thing is that the size and shape of that shadow can test general relativity in the strong gravity regime. It's similar to studying a mountain by examining how it blocks sunlight at different angles. The shadow itself is not the mountain, but it carries information about the mountain's shape. And then there is a fourth language, gravitational waves. When two black holes orbit and merge, they shake spacetime itself. These ripples propagate outward at the speed of light. On Earth, exquisitely sensitive detectors can measure the minuscule stretching and squeezing caused by passing waves. This is not seeing in any ordinary sense. It is closer to listening. Together, these methods, orbital dynamics, electromagnetic radiation, shadow imaging, and gravitational waves, create a surprisingly coherent picture. They point to compact objects with enormous mass concentrated in small regions, consistent with the presence of event horizons. But science doesn't stop at "they exist." It asks, what are they like? Do they spin? How does spin affect accretion? How do magnetic fields shape jets? How does the environment of a black hole evolve over time? This is where multi-wavelength astronomy becomes essential. X-rays reveal the hottest gas and the most energetic processes. Infrared light and optical light reveal stars, dust, and cooler gas. Radio observations trace jets and magnetic structures on large scales. Each band is a different layer of the same environment. JWST plays a special role because infrared light penetrates dust better than visible light, and because very distant light is redshifted into infrared wavelengths. That means JWST can study dusty regions near galactic centers and can probe early galaxies whose signals have traveled across most of cosmic history. Chandra, meanwhile, can isolate high-energy events, flares, shocks, hot halos that hint at how black holes feed and how they influence their surroundings. When you combine these perspectives, black holes become less like isolated monsters and more like central nodes in a larger ecosystem. If you feel the details piling up, return to a simple image. We don't see the wind, but we see leaves move. We feel pressure changes. We hear branches sway. The black hole is the wind in this metaphor. The disk, the stars, the jets, and the radiation are the leaves. Here is a small interaction prompt, very calm. If you could choose only one sense to study the universe, would you choose to see light, hear gravitational waves, or measure motions and forces? If you want, comment one word: see, hear, or measure. Next, we'll scale up to the giants, supermassive black holes in the centers of galaxies, and why they seem to matter for the story of cosmic evolution. One more subtle way we build confidence is consistency across scales. When the same basic model, gravity plus motion plus radiation, explains a stellar mass system in our galaxy and also explains a supermassive system in a distant galaxy, it suggests we are seeing a universal pattern rather than a one-off coincidence. The details differ, but the underlying physics rhymes.
And there is a practical, quiet virtue in redundancy. If orbital dynamics suggest a compact, massive object, and X-rays suggest hot accretion, and radio maps suggest jets aligned with cavities in surrounding gas, and shadow imaging matches relativity, then each line of evidence becomes a check on the others. Science is strongest when it does not depend on a single fragile thread. If you like, think of it as triangulation. In a dark room, one candle might fool your eyes, but 3 candles at different angles can outline a shape. Black hole astronomy is often like that. Multiple instruments, multiple wavelengths, multiple methods, all outlining the same invisible center. Stellar mass black holes are extraordinary,
but they are not the largest characters in this story. In the centers of many galaxies, including our own, there appear to be supermassive black holes, with masses millions to billions of times the Sun's mass. If a stellar black hole is like a hidden boulder in a landscape, a supermassive black hole is like a buried pillar beneath a city. You can't see it directly, but the motion of everything around it reveals its influence. How do we infer a supermassive black hole? One powerful method is to track the orbits of stars near a galaxy's center. If stars whip around a small region at immense speeds, that implies a huge mass is packed into a tiny volume. Over time, careful measurements can constrain the mass and compactness of the central object. In many cases, the required density is so extreme that a supermassive black hole becomes the most plausible explanation. But supermassive black holes have moods. Many are relatively quiet, accreting little matter and emitting modest radiation. Others are fiercely active. When a supermassive black hole is actively feeding, it can produce an active galactic nucleus, an AGN, so luminous that it outshines the combined light of the galaxy's stars. A particularly bright class of AGN is the quasar. Quasars are among the most luminous objects in the universe. The central engine is small in size compared to the galaxy, yet it can flood space with radiation. The power source is not nuclear fusion like a star, it is accretion, the conversion of gravitational potential energy into heat and light as matter spirals inward. This is one of the key insights of black hole astrophysics. Accretion can be extraordinarily efficient. A modest amount of matter falling deep into a gravitational well can release huge energy. If you need a quiet mental picture, imagine a thin stream feeding a spinning wheel in the dark. The stream seems small, but the wheel's motion can light up a large room. Now comes a deeper connection. Galaxies and their central black holes appear to evolve together. Observations suggest correlations between the mass of the central supermassive black hole and properties of the galaxy's bulge, the dense central region of stars. This doesn't mean the black hole controls the galaxy like a puppet master, but it strongly suggests there is feedback. The black hole's activity influences the gas in the galaxy, which influences star formation, which influences the galaxy's growth, which influences the black hole's feeding. Chandra contributes to this picture by observing hot gas in galaxies and galaxy clusters. In some systems, astronomers see cavities, bubbles in the hot gas that align with radio jets. This suggests that jets from central black holes inflate bubbles, pushing and heating the surrounding gas. Heating prevents gas from cooling and collapsing into new stars. In that way, black hole activity can regulate the pace of star formation, shaping the galaxy over billions of years. JWST enters this part of the story by seeing through dust and by reaching far back in time. The earliest stages of galaxy formation are dusty, complex, and distant. JWST's infrared sensitivity makes it a powerful tool for studying early galaxies and the growth of their central engines. It helps identify candidates for early active nuclei and provides spectra that can distinguish between light from stars and light powered by accretion. And here, a modern question becomes especially compelling. Supermassive black holes seem to exist very early in cosmic history. Some quasars are seen at such great distances that we are observing them when the universe was young. How did black holes grow so massive so quickly? Did they start from small seeds and grow steadily, or did some begin as unusually heavy seeds? This is not a settled story. It's an active frontier. Different models propose different growth pathways, and each new data set adds constraints. If you like a calm interaction prompt, what feels most surprising to you about supermassive black holes? Their scale, their central position in galaxies, or their ability to influence star formation from a tiny region? If you'd like, comment one word: scale, center, or influence. Next, we'll move into the early universe and the question of black hole seeds, small beginnings, big endings, and what JWST and Chandra can contribute when the light is faint and the distances are immense. There is also a quiet distinction between mass and influence. A supermassive black hole, even though it is extraordinarily massive, is still tiny compared to the entire mass of a galaxy. The galaxy is dominated by stars, gas, dust, and dark matter. Yet the black hole can matter because it sits at the gravitational and dynamical crossroads. The center is where gas can pile up. The center is where energy injection can heat or expel gas efficiently. So a relatively small fraction of the galaxy's mass can play a large role in setting conditions for the rest. This is a common theme in nature. The smallest parts of a system can govern the flow if they sit at the right junctions. In ecosystems, keystone species can reshape forests. In galaxies, central engines can reshape gas cycles. The black hole is not the whole story, but it can be a powerful punctuation mark in the story. If that feels abstract, translate it into something simple. The thermostat in a house is small, but it affects the whole building. Talking about black holes in the early universe is like talking about a race where the clock is unfair. The universe was young, but some black holes already appear enormous. The time available to grow them seems short, and that mismatch between growth requirements and the age of the cosmos has become one of the most intriguing puzzles in modern astrophysics. To explore it gently, we can introduce the idea of seeds. If you want a giant tree, you can start from a tiny seed and wait. Or you can start from a larger sapling. Black holes may have followed a similar logic. One proposed pathway begins with the first generation of very massive stars. In the earliest cosmic epochs, the chemical makeup of gas was simpler, mostly hydrogen and helium with few heavier elements. Under those conditions, the first stars may have formed differently than stars today. Some may have been exceptionally massive. These stars live short lives and end violently, leaving behind black holes with masses perhaps tens to hundreds of solar masses. If light seeds are the beginning, then growth must be rapid. Black holes grow by accreting matter and by merging with other black holes. But accretion is not unlimited. As a black hole feeds, the surrounding disk can become so luminous that radiation pressure pushes infalling matter away. This creates an effective cap, at least under many conditions, on how fast a black hole can grow. Over long periods, steady growth is possible, but for the earliest quasars, steady growth from a small seed can feel too slow. This leads to another pathway: heavy seeds. In some environments, a large cloud of gas might collapse directly into a massive object without fragmenting into many ordinary stars. Under special conditions, such as strong radiation backgrounds that suppress cooling and fragmentation, a gas cloud could form a very massive central object that collapses into a black hole with a much larger initial mass. If you start with a heavier seed, the race becomes easier. JWST is especially relevant here because it can see very distant galaxies and active nuclei by observing in infrared. Light from the early universe is redshifted, stretched to longer wavelengths as the universe expands. JWST's instruments are designed to capture precisely that. By identifying early galaxies and measuring their spectra, JWST helps constrain the presence of active black holes and the conditions of early star formation.
Chandra complements this by observing X-rays, which can be a signature of accretion onto black holes. However, the early universe is complicated. Gas and dust can absorb X-rays, and distant sources can be faint. Still, in some cases, X-ray detections can strengthen the case that a distant source includes an actively feeding black hole rather than being powered only by star formation. A key point, calmly stated, is that new data does not always deliver a single interpretation. A bright infrared source might be a galaxy forming stars at an extraordinary rate, or it might include an accreting black hole, or both. Dust can mimic certain signatures. Emission lines in spectra can help disentangle these possibilities, but uncertainties remain, and science advances by narrowing them. When people say JWST is revealing the early universe, part of what they mean is that it is revealing the complexity, forcing models to accommodate objects that look surprisingly mature, surprisingly structured, or surprisingly luminous at early times. That doesn't mean old theories were wrong. It means the parameter space is wider than we assumed, and the universe is comfortable surprising us. If you're listening in the dark, let this be a soft thought. The early universe was not a simple blank slate. It was dynamic, energetic, and full of unevenness, over densities, turbulence, radiation backgrounds, and rapid changes. In such a setting, black holes might have grown in bursts, or in rare extreme environments, or through pathways that are uncommon today. Here's a gentle interaction prompt. When you imagine black holes growing early, what feels more intuitive? Many small seeds growing steadily, or fewer heavy seeds forming in rare conditions? If you want to comment, just write many small or few heavy. Next, we'll shift into an even more famous puzzle, one that sits at the border of gravity and quantum physics: Hawking radiation, black hole evaporation, and the question of where information goes. Another reason the early universe question is so compelling is that it forces us to combine many uncertainties at once. We have to model how gas cools, how it fragments into stars, how radiation from the first stars changes the chemistry of the surrounding medium, how dust forms, and how mergers build larger structures. Black hole growth sits inside this web. A small change in one part, say how efficiently gas loses heat, can alter which pathway dominates. JWST helps by turning some of those uncertainties into measurements. Spectra can reveal the chemical fingerprints of early galaxies. The shapes of emission lines can hint at winds and outflows. The distribution of light can show whether a system is compact or extended, smooth or clumpy. Each observation is a constraint, and constraints are how models become sharper. Chandra's contributions, even when detections are difficult, also matter because non-detections can be informative.
If you do not see strong X-rays from a certain class of objects, that sets limits on how many of them could host powerful, unobscured accretion. Limits do not feel exciting in headlines, but they are the calm backbone of scientific progress. And all of this connects back to a larger theme. The universe may grow its most extreme objects not by one universal method, but by multiple methods that dominate in different environments. The early cosmos might have favored rare, extreme pathways that are uncommon now. Now we arrive at a paradox that can be stated in a whisper, yet it echoes through physics. A black hole is defined by the idea that nothing escapes from inside the event horizon. And yet, quantum physics suggests that black holes may not be perfectly black. They may emit an extremely faint radiation, so faint that for astrophysical black holes, it is essentially undetectable with current technology, but still profound as a principle. This is often called Hawking radiation. A gentle way to describe the idea is to talk about quantum fluctuations. In quantum field theory, empty space is not truly empty. Fields have restless fluctuations. Pairs of particles and antiparticles can appear and vanish on very short timescales. Normally, these virtual pairs annihilate almost immediately, leaving no lasting trace. Near an event horizon, the story can change. Under certain interpretations, one particle of the pair can fall in, while the other escapes to infinity. To an observer far away, it looks as if the black hole emitted a particle. And because energy must be conserved, the black hole effectively loses mass. Over an extraordinarily long time, that implies the black hole can evaporate. On its own, this would already be remarkable, but the deeper issue is information. In quantum mechanics, the evolution of a closed system is, in a strict sense, reversible. Information about the initial state is not supposed to be destroyed. It may become scrambled and hard to retrieve, but it is not erased from existence. Now imagine throwing a complex object, say a book, into a black hole. If the black hole later evaporates away into featureless thermal radiation, it seems the detailed information contained in the book is gone. The final radiation looks too simple to encode the original complexity. This appears to violate the quantum rule that information is preserved. That tension is called the black hole information paradox. It is not merely a trick question. It is one of the clearest signs that our two greatest theories, general relativity and quantum mechanics, do not fit together perfectly in extreme conditions. How do physicists respond? With several ideas, each with its own elegance and difficulty. One possibility is that information is preserved, but it is encoded in the Hawking radiation in an extremely subtle way. In this view, the radiation is not perfectly thermal when you account for all quantum correlations. It only looks thermal if you ignore the fine-grained structure. The information is present but scrambled. Another idea points towards the concept of black hole entropy. Black holes behave like thermodynamic objects. They have temperature and entropy. Strikingly, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This suggests that the number of microscopic states, the hidden details that entropy counts, is connected to the horizon's surface. That area scaling inspires the holographic principle, the idea that information in a region of space can be described by degrees of freedom on its boundary, like a three-dimensional world encoded on a two-dimensional surface. In this picture, the event horizon is not merely a geometric boundary, it is a kind of information ledger. Then there are more radical proposals. Some suggest that the event horizon might not be as smooth and eventful as relativity predicts for a freely falling observer. The firewall idea proposes that to preserve quantum consistency, an infalling observer might encounter high-energy phenomena at the horizon. Another family of ideas, sometimes discussed under concepts like fuzzballs in string theory contexts, proposes that what we call a black hole might actually be a complex quantum object with no empty interior in the classical sense. These proposals are not settled facts, they are attempts to heal a real wound in our theoretical framework. And the calm attitude is to treat them as active research, not as conclusions to sell, but as possibilities to explore. If you're listening in a sleep-friendly way, keep the metaphor simple. A black hole might be less like a trash can that destroys a message and more like a machine that compresses it into an unreadable code. Over time, the machine leaks that code back out. The code looks like noise unless you have the key. The key may be the subtle correlations across the radiation, or it may be something deeper that we have not yet fully understood. Here's a gentle interaction prompt. When you hear information, do you imagine it as living inside things or on the surfaces and relations between things? If you want to comment, write inside or surface. Next, we'll return to relativity with a calm thought experiment. What would you experience near a black hole? How does time behave? How does light bend? And why singularity may be less a place than a sign that new physics is needed. One way to stay grounded is to remember what makes the paradox a paradox. It is not that we don't know what happens inside. It is that our best theories make conflicting demands about what should be allowed in principle.
Relativity, in its cleanest form, says the horizon can be smooth for a free-falling observer. Quantum mechanics, in its cleanest form, says information is not destroyed. Hawking evaporation, taken at face value, seems to threaten both simultaneously. That is why black holes are sometimes called a laboratory for quantum gravity. We cannot build a black hole in a lab, but nature has built them for us, and the logic of our theories forces us to pay attention. You may also notice that many proposed resolutions rely on correlations, subtle relationships between parts of a system that are not obvious if you look only at averages. This is a familiar idea in everyday life. You can learn nothing from a random-looking sentence unless you know the grammar that ties the letters together. Quantum correlations can be like grammar. They can make a seemingly thermal signal carry hidden structure. Tonight, you don't need to solve it. You only need to sense why it matters, because it is a question about whether the universe keeps faith with its own rules. Imagine you are far from a black hole. From that distance, it behaves like a dark mass. You can orbit it. You can compute trajectories. Gravity feels familiar. But as you approach, relativity begins to feel less like an equation and more like an environment. One effect is gravitational time dilation. In strong gravity, time passes more slowly relative to a distant observer. This is not a metaphor.
It is a measurable feature of clocks in curved spacetime. Near black holes, the effect can be extreme. This leads to a famous comparison between viewpoints. Suppose you fall toward a black hole while a friend watches from far away. Your friend may see your fall appear to slow down as you near the event horizon. Light from you becomes redder and dimmer. In the distant observer's description, you never quite cross the event horizon within a finite amount of their time. Instead, you fade. But in your own experience, you can cross the horizon in a finite, proper time. You don't necessarily notice a dramatic boundary at the moment you pass it, at least not for a sufficiently massive black hole where tidal forces at the horizon are gentle. This is one of relativity's quiet lessons. Different observers can describe the same reality differently, and those descriptions can be consistent as long as they respect what information each observer can access. Light behaves strangely near a black hole too. In ordinary life, light travels in straight lines. Near strong gravity, the straightest possible paths, geodesics, are curved. Light can bend around the black hole. It can loop, creating multiple images of the same background. It can form arcs and rings. If a glowing accretion disk surrounds the black hole, gravitational lensing can make the far side of the disk appear above and below the hole, as if the disk is wrapping itself into view. These are not just artists' impressions. They are calculated predictions of general relativity. And when observations align with these predictions, confidence grows that we truly are seeing space-time geometry at work. Then there are tidal forces, the difference in gravitational pull across an object. Gravity decreases with distance. If your feet are closer to the black hole than your head, the pull on your feet is stronger. That differential can stretch objects along the radial direction. In popular descriptions, this is called spaghettification. For small black holes, tidal forces near the horizon can be intense. For supermassive black holes, the horizon can be so large that tidal forces at the horizon are relatively mild, at least initially. And then we reach the word singularity. In the simplest solutions of general relativity, the center of a black hole contains a point where curvature becomes infinite. But many physicists interpret this not as a literal physical point of infinite density, but as a sign that the classical theory has been pushed beyond its domain. When a model produces an infinity, it may be telling you it needs an upgrade. This is a healthy scientific attitude. History is full of infinities that dissolved when deeper frameworks arrived. It is very possible that a future theory of quantum gravity will replace the classical singularity with a more complete description, perhaps a region of extreme but finite density, perhaps even something more subtle. If you're listening at night, you don't need to picture the singularity as a terrifying object. You can picture it as a question mark, a punctuation mark at the edge of our current understanding. There's also a quiet emotional truth here. The event horizon is a boundary of observation. It reminds us that knowledge can have edges. And that is not only a limitation, it is also a kind of structure. Boundaries shape ecosystems. Boundaries shape stories. Boundaries shape what can be asked and what can be answered. If you want a gentle question, Do you find it beautiful or unsettling that two observers can describe horizon crossings so differently? If you want to comment, just write beautiful or unsettling. Next, we'll step into the speculative zone. Not to claim certainty, but to appreciate how humans think when they're trying to stitch together relativity and quantum physics. Wormholes, holography, and other attempts to understand black holes at the deepest level. There is another gentle effect, gravitational redshift. As light climbs out of a gravitational well, it loses energy and shifts to longer wavelengths. Near a black hole, this can be dramatic. It means that the inner disk can emit very energetic photons, but by the time those photons reach a distant telescope, their energies are altered by gravity and motion. This is why interpreting spectra from near black holes requires careful modeling. The signal is a mixture of heat, speed, and geometry. In a calm way, you can think of it like listening to a song played while someone is moving away from you. The pitch changes, the sound stretches. You can still infer what the original song was, but you need to account for the motion and the distance. Around black holes, the motion is orbital speed near light, and the distance is the depth of space-time curvature. These effects are not just complications, they are opportunities. They give astronomers tools to estimate spin, disk structure, and the properties of the inner flow, without ever crossing the horizon. When a mystery is deep enough, it becomes a meeting place. Black holes are one of those places, where well-tested physics meets ideas still under construction. One idea often mentioned in popular culture is the wormhole, a hypothetical tunnel connecting distant regions of space-time. In certain mathematical solutions, wormholes can exist as geometrical possibilities, but keeping a wormhole open and traversable typically requires exotic conditions, forms of energy or stress that behave differently from ordinary matter. As of now, wormholes remain speculative. They are useful, though, because they help physicists ask what space-time is allowed to do in principle. Another major idea, discussed more seriously in modern theoretical physics, is holography. The holographic principle suggests that the information content of a volume of space can be represented on the boundary of that volume. The area-entropy relationship supports this kind of thinking. If entropy, and therefore the number of microscopic states, scales with area, not volume, then perhaps the inside is not where information fundamentally lives. Related to this is the notion of complementarity, the proposal that descriptions from outside the horizon and from inside the horizon can both be valid, even if they seem contradictory, because no single observer can access both sets of information in a way that allows a direct comparison. In this view, the universe does not violate consistency. It limits the conditions under which contradictions could be exposed. There are also proposals that try to resolve the information paradox by modifying what we assume about the horizon itself. The firewall concept suggests that an infalling observer might encounter high energy effects at the horizon, sacrificing the traditional expectation of a smooth crossing in order to preserve quantum consistency. Other approaches, such as fuzzball-like pictures in some string theory contexts, suggest that a black hole could be a complex quantum object with no empty interior as classical relativity imagines. So how do we test such ideas? We look for observational consequences that differ from classical expectations, even subtly. For instance, the way matter behaves very near the horizon may produce signatures in X-ray timing and spectra. The gravitational waves from black hole mergers might carry faint echoes if the near-horizon structure is different from the classical picture. These are challenging tests, but the history of science is full of situations where what once seemed impossible to test became testable with patience and better instruments. In this context, JWST and Chandra are not direct wormhole detectors, but they improve the foundational picture. They characterize accretion environments, the growth of black holes across cosmic time, and the interplay between black holes and galaxies. Better context means tighter constraints. Tighter constraints mean fewer viable theories. In that way, data combs through speculation and leaves behind the strands that can withstand reality. There is also an important stylistic point, especially for a calm documentary channel. When we talk about speculative ideas, we should use careful language. Might, could, is proposed, is debated. That doesn't make the story less interesting, it makes it more honest. Mystery is most compelling when it is not forced. If you're listening while drifting towards sleep, you can treat this speculative zone as a gentle dreamscape, a tunnel through space-time, a universe encoded on a surface, a boundary that carries the memory of what fell in. You don't have to believe any of it tonight. You can simply notice how far the human mind is willing to go and how it tries to stay disciplined even when imagination is strong. Here's a calm interaction prompt. Which idea feels most intuitively beautiful to you? The tunnel, wormhole, the surface, holography, or the hidden complexity, fuzzball-like pictures? If you want to comment, write one phrase: tunnel, surface, or complex. Next, we'll close the episode the way we began, slowly. We'll look forward to what future observations may bring, and we'll end with a quiet sense that black holes are not only cosmic mysteries, they are also mirrors for the limits and the elegance of human understanding. It's also useful to remember that speculation in physics is not a free-for-all. It is constrained imagination. The best speculative ideas are those that preserve what is already well tested, explain something that seems inconsistent, and make new predictions that could, in principle, be checked. That last part, testability, matters. A wormhole story is interesting, but a scientific wormhole story becomes more interesting if it connects to observable phenomena, even indirectly. Likewise, holography becomes powerful when it provides a mathematical framework that reproduces known results and suggests new ones. In the near term, many tests will come from precision, better timing measurements, sharper imaging, cleaner gravitational waveforms, longer monitoring campaigns. The universe may not give us a single dramatic clue. It may give us 1,000 subtle ones, each a small nudge toward the right theory. This is a very quiet universe kind of progress, patient, cumulative, and deeply satisfying if you enjoy the slow sharpening of a picture. If you've stayed with this episode all the way here, your mind has traveled a long arc without needing to rush. We began with the simplest idea, a boundary in space-time. We moved through history, through accretion disks and jets, through the instruments that observe the hot and the distant, and then into the paradoxes that arise when quantum rules meet gravitational extremes. Now let's close by asking a quiet, practical question. What comes next? In astronomy, the next chapter often comes from two directions. The first is better observation, seeing clearly across more wavelengths and across more time. The second is better theory, models and simulations that connect these observations into a coherent, testable picture. On the observational side, we will keep watching the environments around black holes with increasing precision. X-ray observatories can follow flares and measure timing variations that tell us about the inner disk. Infrared observatories can see through dust and reach back toward the earliest stages of galaxy growth. Radio arrays can map jets and magnetic structures across enormous scales. And gravitational wave detectors will continue to expand the catalog of black hole mergers, turning rare detections into a steady stream of cosmic sounds. On the theoretical side, the grand challenge remains: reconciling relativity and quantum physics. Black holes may not be the only place where quantum gravity matters, but they are the most dramatic place where the mismatch becomes unavoidable. Any genuine theory of quantum gravity must be able to explain black hole entropy, black hole evaporation, and the fate of information in a way that does not contradict what we already observe. While we wait for a deeper synthesis, we can still appreciate what is already clear. Black holes are natural outcomes of gravitational collapse under extreme conditions. Their presence can be inferred through the motion of stars, the glow of hot accreting gas, the silhouettes formed by lensing, and the ripples of gravitational waves. And their influence is not confined to their immediate neighborhoods. Through jets and radiation, black holes can shape the evolution of galaxies and clusters over billions of years. If you'd like a gentle image to carry into sleep, choose one that is calm, a thin ring of light surrounding a round, quiet shadow. A disk of faint glowing mist turning smoothly in the dark, or a long, steady jet stretching outward like a line drawn across space. Let the image be slow, let it breathe. Here is a final soft question if you're still awake. Among all the mysteries we touched tonight, which kind of mystery do you naturally prefer? The mystery of the early universe, how things formed so quickly? The mystery of space-time, what geometry really is? Or the mystery of life, whether anyone else looks up and wonders the way we do? If you want to comment, write one word: early, space-time, or life. And now we can let the episode fade. If the quiet universe fits your nights, you can support the channel in a very gentle way. Leave a like, subscribe, and share this episode with someone who also enjoys calm, science-based stories. That simple support helps this series continue with more long, quiet episodes designed for rest as much as for curiosity. Thank you for listening. Thank you for being here. May your breathing slow, may your thoughts soften, and may you sleep well under a sky that is vast, patient, and quietly full of wonder. Before you drift fully into sleep, it can help to end with a simple reframe. A black hole is not a threat hanging over the night sky. It is a feature of the universe's architecture, rare, distant, and deeply informative. Most black holes are far away, Most are quiet, and even the active ones are valuable precisely because they illuminate how gravity, matter, and magnetic fields behave at their limits. It's also something emotionally steadying about boundaries. The eminent horizon is a boundary of communication, not a boundary of meaning. It tells us where our current methods stop working and where new methods must begin. In that sense, it is not a wall, it is a signpost. If you return to this episode on another night, notice how your curiosity changes with your mood. Sometimes the history feels comforting. Sometimes the paradox feels intriguing. Sometimes the imagery of the disk and the ring feels like a lullaby. Science, at its best, can be a form of calm attention. And if you'd like, you can save this episode to your playlist for nights when you want your thoughts to have a direction, but not a rush. Thank you again for listening.
And if you take only one scientific idea from tonight, let it be this. Black holes are understood best by what they do to their surroundings. We measure motion, we measure spectra, we measure timing, we measure shadows and ripples. The black hole itself is quiet, but it writes signatures into the light and the geometry around it. That means you can enjoy black holes in a calm way. You don't have to imagine falling in. You can imagine standing far away with patient instruments, watching a ring of light, a steady jet, a star on a tight orbit, or a waveform that rises and fades. In those signatures, the universe tells us a story that is both precise and peaceful, if we let it be. If you're ready to sleep, let the last thought be simple. The cosmos is larger than your worries, and it continues its slow work in silence. Good night.